Hello, everyone, and welcome to our third think tank of the 2024-2025 academic year. Today we have Dr. Kiva Oken coming in to give us another presentation. She is another SATS alumni and another Putnam Lab alumni, and she's going to be talking about when environmental drivers improve stock assessment outputs from models. So without further ado, I'll let Kiva go ahead, take it away. And if you have any questions, feel free to go ahead and speak up or ask in the chat. I will be taking questions throughout. So Kiva, take it away.
Yeah, thanks, Will. So like Will said, feel free to ask questions throughout. I don't think this is going to take a full 2 hours, so you can go back to like doom scrolling despite absolutely no new information in no time. Before we get started, just a public service announcement. Today is election day. If you are eligible to vote, which I don't think everyone in this room is, so if you are eligible to vote, I encourage you to vote. Ballots must be postmarked today or dropped off at a drop box by 8 p.m. I learned that you can register. Washington has same-day voter registration, and there's a registration location right at the Husky Union and many other sites in King County. The King County elections website has a lot of great information. Also, in honor of the election, I'm using the inauguration, our color palette in some of these figures. All right. So I think, it's not really wild to say that the environment is a really important driver of the dynamics of fish populations. But I also think it's important to go a step further and say a better understanding of relationships between the environment and fish populations should improve our scientific advice that we give to management, and is particularly true with the advent of climate change. So recruitment is a really important, really variable part of a fish population's history. And in order to understand recruitment, first maybe we should understand how many spawners there were. Maybe that will predict recruitment, but stock recruit relationships tend to be quite weak. So Pacific hake is a particularly variable population with particularly variable recruitment. And you can see, oh wait, let me get the little pointer. So you can see, we have years like 2010 where we had very low spawning biomass and a total bumper year of recruitment. And then there's also many years with very high spawning output and really low recruitment. So spawning output, not a great way to predict recruitment. Age composition data is a really useful way to inform estimates of recruitment, but it takes time. So here I was very excited to include a figure from Johan Hjort in my talk. There was a really large year class of herring in 1904. In 1907, you can see there's maybe like a little bit more daylight than usual of age 3 fish. In 1904, in 1908, there's a spike of age 4 fish, but that could still just be sampling error. We're not sure yet. Then in 1909, we see that year class again as age 5, and it's really huge as age 6s in 1910. So at this point, maybe like 5-6 years after these fish are born, we're sort of confident that there was this large year class in 1904. So repeated observations can be used to estimate recruitment strength. They're very good at that, but it takes time to establish year class strength. And it would be really nice, especially sort of to provide forecasts to managers, if we could provide this information sooner. Oceanographic data could provide recruitment information earlier than composition data. So if we can develop relationships between what's going on in the ocean and what the fish populations are going to do, and we have information, sort of real-time information on what the ocean is doing, we can provide much earlier predictions of when we're going to have large and small year classes. And there are there's sort of 2 main ways that this oceanographic data tends to enter stock assessments and inform recruitment estimates. So the first is the environment as an index. So here we have sort of a generic stock recruit function that's a function of spawning output, and then we have just some random noise that it gets multiplied by. And then we assume that our environmental time series is just an observation of these epsilons of this sort of recruitment variability with some amount of error that's determined by sigma. The other option is to include sort of our environmental oceanographic data directly within the population model. So now, instead of having recruitment only as a function of spawning output, we have recruitment as a function of spawning output and what the environment is doing, multiplied by some noise. The problem with this is sort of the process research that we do to identify environmental drivers. We're not going to identify the actual correct environmental driver that's driving recruitment. We're going to get something kind of close-ish. So we don't really want to use in this recruitment function the environmental driver that we're observing. So usually the way this is implemented is with a state space framework. So the true environmental driver is what drives recruitment, but our observation of the environmental driver is a random process. And then you impose some sort of auto-regressive process on the environmental driver in like a state space approach. So this works very well. The downside to this, is that you generally need to use random effects to estimate, to sort of conduct estimation of this model. And so a lot of assessments, including all West Coast assessments, are still being done in stock synthesis, which is based in ADMB, which does not estimate random effects. That is one sort of issue with this approach. And the other issue is we often fix the variability of these epsilons. And the variability of this epsilon is going to be greater than the variability of this epsilon because the environment, in this case, is going to soak up some of that variability. And there's not really good guidance on sort of how to tune that recruitment variability when you include an environmental driver. So on the West Coast, we have sort of opted for this environment as index approach. And so that's sort of what I'm going to focus on today. But I think some of the conclusions at the end are sort of generic to the approach. So I think it's really exciting to sort of do all this process research and identify these drivers, but it's also important to figure out how to sort of specify them in a stock assessment and think about what kind of stock assessments we want to include them in. So I think a few sort of outstanding challenges, not in sort of the process research side of things, but actually in sort of putting these indices in stock assessments, is that I'm not sure we've quite defined what improvement we want the index to provide and also how to measure that improvement. I think we haven't really thought about if there are any drawbacks to doing this. And I think there's just not really like a best practice that's been established for including environmental recruitment indices in assessment models. So that's sort of like what I wanted to sort of go forth and think about. And so sort of the big question for this talk then is sort of how do environmentally based indices of recruitment influence stock assessment advice? I took 3 different approaches. The first was to fit retrospective models with and without simulated recruitment indices. The short version is this didn't work, but I also think it's important to talk about the full research project and all of the dead ends that we hit along the way, since Think Tank is sort of a works in progress seminar. So I'm going to talk about this briefly. Because that didn't work, then I tried simulating known populations and fitting assessments with and without recruitment indices. And then I'm going to sort of apply some of what I learned from the simulations to an operational model that had a true environmental index developed for it, or not true, but had an environmental index developed for it. All right, so I'll start with this. So when I say I did this, it was actually a very intrepid undergrad who did an awesome job a few summers ago, named Rachel Wren, who's now in grad school at UT Austin. And so what we did was we took a time series of recruitment. And so this is a full, I think this is from the Hake assessment. And so we assumed the full time series out to 2020 is sort of truth. And this is sort of our best guess at what recruitment is. And now you imagine that it's 2005. You just started watching this show, Grey's Anatomy. Who knows how long it'll be on for, maybe a few more years. And we cut off the data in 2005. And then we refit the stock assessment model just as it was without an environmental index. and then simulated environmental index off of these, quote, true blue recruitment deviations. And so that's yellow is with the environmental index. And then we measured the error between sort of our short assessment model fit of the final we measured the error of the estimate of recruitment in the final year with and without this sort of simulated environmental index. There were a few issues with this approach. First is that most West Coast fishery independent surveys were quite new in 2005. And so when we cut off the data, we're not just shortening the time series, we're really fundamentally changing the nature of the data that's in the assessment. Second is that default retrospective functions don't handle time varying selectivity well. And if you're going back 15 years, you're often sort of looking at different selectivity blocks and that sort of thing. The elephant in the room that we don't actually know recruitment in 2005. And then just in general, we were just applying these to production stock assessment models. They're fairly complex, and so it was a little hard to figure out what was going on. So then I was like, I think maybe I talked to Andre, and he was like, you need to just simulate these populations so you know what recruitment is. Which is a very Andre thing to say. And so then I was like, Rachel went on to grad school, and I was like, okay, let's just like actually simulate these populations so we sort of know exactly what's happening. So I used the SS3 sim package to simulate a full population trajectory and then randomly sample from that population and refit the assessment and fit the assessment model. I did that 100 times across a bunch of different scenarios. Right now, today, I'm going to show this for two species. So one is an Atlantic cod, which is sort of built into the SS3 sim package. And then the other one is a very simplified version of the Petrale sole, the 2023 Petrale sole stock assessment. Both of these, in both of these assessments, the survey, there is a fishery independent survey that first observes the population around age 3. This was probably not optimal. It would have been ideal to have a range of those ages. I think the cod is very sustainably fished. I think it only hits like 50% of its unfished biomass, whereas Petrale was fished very heavily in like the 70s and 80s. It has since recovered to its target around 25% of unfished biomass. And then cod is a bit shorter lived, so the natural mortality is 0.2 versus 0.14. And then it also has a lower steepness and a lower recruitment variability. So in general, we would expect spawning output to explain a greater fraction of variability in cod recruitment than Petrale recruitment, which is going to, spawning output's not going to predict Petrale recruitment as well. So I have these sort of simulated populations, then you sort of sample data from the populations. The data for Petrale was sampled with the same intensity that we actually sample from it in real life. And then I included an environmental recruitment index of varying quality. So I just took the recruitment deviations that were simulated and then simulated a recruitment index on top of that with some amount of standard error and just varied that standard error. So this is just an example of one single simulation. This is for cod. So for cod, I think the population is simulated for 25 years unfished, and then fishing turns on, and that's also when the data starts to get collected. The population gets fished down very rapidly, and then it basically bops around until year 100. And in year 100, the operating model continues to run, but you stop collecting data. So the only data that's provided after year 100 to the estimation model are the catches. And so here's what we see. This is basically this would just be a normal stock assessment model with no recruitment index. And this is sort of the main data period of the model. It does a pretty good job recreating the dynamics of this population, which is good because everything is correctly specified. But now if we look at the forecast period, we can see that the population sort of declined during the forecast period, and that our assessment forecast missed that decline. So now if we look at all of the models, so now as the colors get bluer, they become sort of more and more, have a more and more informative recruitment index. And we see that the bluer the color, basically the better job we do at tracking this downturn in the population during the forecast period. So what happened was there was sort of a recruitment failure towards the very end of the data period of the model. So there's no composition data to inform that, but the oceanography, or our fake simulated recruitment index, did have information on that recruitment failure. And so the models with the more informative recruitment indices are able to capture that downturn in the population. Obviously, this was a cherry-picked example that worked very well. So let's now look at what happens over a whole bunch of simulations. So now on the x-axis, we have the index standard error, and on the y-axis is the first thing I wanted to look at is the relative error of recruitment in the terminal year. So we would expect that these recruitment indices are going to sort of improve our ability to estimate recruitment in the terminal year, which is generally very difficult to estimate. We very rarely have sort of composition or index data that can inform estimation of recruitment in the terminal year. So we see, and what we would expect to see, right, is we would expect to see what we're looking for is a distribution that's centered around 0 and that's very short and squat. And that is basically what we see. So as we have more and more informative recruitment indices, that we do a better job estimating terminal year recruitment for the most part. If you look now we're looking 20 years back from the terminal year. And we see for cod, basically we have a lot of really good composition data that's complete, so the recruitment index doesn't help us estimate recruitment in year 80 because we have 20 years of composition data to help us estimate recruitment in year 80. And in fact, we see some outliers where it's estimated worse. And I think what's happening there is even though the recruitment standard error is 0.05 and that's correctly specified and input into the model, so it's going to have a lot of weight in the likelihood, you can still simulate something out in left field and simulate something wrong. And so I think that's what's going on here is you have a low standard error, but you still every once in a while are going to simulate something wrong. With petrale, we actually see this is sort of the first indication that something a little bit weird might be going on. So we see increasing bias in the estimate of this terminal year -20 recruitment as the standard error goes up. So we're doing it without the index. We do a fine job. It's generally unbiased, and then it's positively biased. It gets more and more positively biased as you move left. So now, so that was just sort of 2 years cherry picked out. So now I wanted to look at like the full time series and particularly look at the forecast period. So how are we doing at forecasting the population? Because the forecast is, one of the key components of what we're using for management advice. So we need to estimate reference, we need to estimate reference points, and the reference points are based on the hindcast, but we're also basing it on current status, and the current status is based on the forecast. So now we're looking on the x-axis is time. They have different time periods, which is a little confusing, but they both are run for about the same amount of time. And now on the y-axis is mean absolute relative error of spawning output, so you want to be close to 0. And the forecast period is in gray. So during the hindcast, so now this is the data period of the for cod. We see that pretty much all these lines look very similar. We do see as you go farther back, they actually spread out a little bit, and you're seeing lower error without the index than with the index, but these lines look fairly similar. Petrale is doing some wild stuff. And these are also different. The y-axes are also different. So it's really wild stuff. And so, what's happening, this is the period with basically no data. So this period of the petrale model, basically you just have catches. That's the only thing in the model. And the catches are very high. The population being fished very hard at this time. But yeah, so this is a little crazy. Once you have data, then sort of all the lines sort of converge to one another. So, because the data starts around 1980, or the composition data. All right, so now let's look at the forecast. For cod, you can see that there is a mild improvement in the forecast when you include the environmental index. It's I think small, but it's definitely there. So you see lower mean absolute relative error with these bluer lines. And then the error gets larger as you are forecasting farther and farther into the population. With petrale, you sort of see a similar effect, except there's some weird stuff going on with the 0.05 and 0.1 scenarios, particularly early in the forecast. And you also, the other thing I noticed is there's sort of a wider divergence across these lines with petrale than with cod. And I think that's because they're longer lived. And so with cod, you know, you're forecasting 12 years out. By 12 years from the end of the stock assessment, there's very few fish still alive that were alive during the estimation period. And so there's just like not as much benefit, but there is still a benefit, you know, earlier in the forecast period, there's more of a benefit. And I think, you know, on the West Coast, our standard is to forecast for 12 years, but for a cod life history, you probably shouldn't be using a 12-year-old forecast. All right, so this is some crazy stuff that's going on with petrale though. So sort of digging into it a little bit into specific parameter estimates. So now this is the relative error of unfished recruitment, and we see that as the index becomes better and it's like more informative, we see this increasingly positive bias in unfished recruitment. So petrale, the cod model fixes natural mortality, but the cod model estimates natural mortality. So I only have this for cod now, or sorry, this figure only exists for petrale, but we see the same pattern with natural mortality, where it's increasingly positively biased as the index becomes more informative. So what is causing this bias? Things I have investigated and ruled out are bias correction ramp. So I tried fitting a single simulation using MCMC, and the estimate of R0 was basically completely unchanged. Steepness is too low. I've done this like steepness up to like 0.95, nothing changes. I've tried fixing catchability. I've tried estimating catchability. I've tried the sum to zero recruitment deviation constraint off. I've tried it on. None of these things seem to be impacting it. I have not yet solved this. If you have an answer, I would be very interested. However, I did some likelihood profiles, and it was really clear that, you know, these indices were just having a really strong pull on the likelihood. And so I was like, well, we don't need the index, you know, 20 years ago. It's what's it doing in, you know, the year 2000? So I was like, what happens if we just cut off the index, you know, and only include it for 10 years? So previously, for all of the models I've shown you so far, there was 30 years of the environmental index, which is pretty realistic. A lot of our ocean models start around 1990, so we often have about 30 years of oceanography available. But what if we just include it for 10 years? So now here what you're seeing is the relative error of unfished recruitment as I showed you before. So the light colors, you've already seen these distributions. And now the saturated colors are what happens if you only include the index for 10 years. And this bias is basically gone. So basically I have not actually identified the mechanism of this bias, but if you reduce the weight of the index and the likelihood in sort of a smart way so that it can sort of provide the information that that the index is uniquely qualified to provide without sort of gumming things up earlier in the time series, that works.
And Kiva,
yeah.
when you say weight,
yeah.
the index, I assume it's using the appropriate length of the index. Is that how doing the weight, or?
So I guess the data weighting, I mean, the weight of the index is the standard error of the index, yeah. and then also, but it's going to be a larger likelihood component if you have 30 data points with a standard error of 0.05 rather than 10 data points. Yeah, so I'm not actually changing doing any sort of fancy data weighting, just like fewer data points. Yeah. And the same thing is true of natural mortality. That bias also basically goes away when you shorten the time series.
I'm
Yeah.
just curious, your satellite era comment is absolutely true.
Yeah.
Problematic. There are other proxy data sources that we use.
Yeah.
That go back much earlier.
Yeah. I think that would be worse though.
Yeah, it would be interesting to know if you had stable digits on the West Coast
Right.
as this example, right, where you could have catch in the environmental index, which is a weekly correlative thing, before your other data start.
Yeah.
Should you or should you not use it? Here you're saying maybe not.
Right.
But it's an open question, I think, whether if you have a longer time series of the climate index,
Mm-hmm.
should you or should you not use it earlier in the time period rather than assuming some average recruitment?
Yeah.
It's noisy.
I guess, I mean, it would be easy to simulate these for 100 years instead of 30 years,
Yeah.
but my guess would be that this bias would just get worse. Well, I mean, and again, it also depends on how strong the index is. But I think I would not include these for a lot of years.
Yeah, and I think this is a really important
Yeah.
question.
Yeah.
And I wonder, another way of looking at this is if you simulated, you say the trolley.
Yeah.
And have the environmental index start much earlier.
Yeah.
When you don't have any composition data.
Right.
And then as soon as you get composition.
Turn it
data,
off.
Turn it off and then turn it back on at the end.
Yeah. Yeah.
And see if this pattern bias
Yeah.
is present.
Yeah.
Matters.
Yeah. Yeah. That's a good idea. I should write this down somewhere. I could just watch the video later and like complain about how awful I sound. Yeah, I think that's a great idea. That's the joy of simulations. And then so then you can also look at the time series. And so this like really just wild stuff goes away when you shorten the time series. And even in the forecast period, I mean, this is not a great figure. It's kind of hard to see what's going on. But there were some like weird things going on early in the forecast with the particularly skillful indices and that sort of go down. Yeah, Melissa.
I'm just curious, if those runs that are like really focused looking.
I mean, it's 100 runs. It's the average of 100 runs.
What parameter estimates were changing, like were other parameter estimates changing? Was something really ill-behaved in those? I guess my question.
So I have run, these are all bias corrected, and so the Hessians all invert. So that they're not, does that answer?
I'm just saying, you compared like the runs that seem to be well-behaved with the ones that aren't, and what parameter estimates were different.
So yeah, I think I think
Only
yeah, I mean, growth, it doesn't change a lot. Growth is pretty stable. So it's really, yeah, the scale and the natural mortality. I guess I haven't looked at selectivity, but
yeah, I mean, the trolley is probably asymptotic, so it's
yeah,
a little more locked down than others.
yeah, but it's not growth. Yeah, so, but I think those are what's sort of going awry.
Yeah, and a quick clarifying question from the chat. Can you
Yeah.
remind us how recruitment itself is treated? Is there also a stock recruit relationship?
Yes, so there is a stock recruit relationship. Yeah. And steepness is fixed in everything. Correctly.
Yeah, because just kind of looking at this, you would kind of guess recruitment is going awry in those early years, recruitment deviation.
Mhm.
But there's no data period. Yeah, so I'd be really surprised if it wasn't, coming up, essentially
The
for
stock.
uncertainty.
Right, and the stock, and basically, you're getting, you have the stock recruit relationship wrong because R0 is wrong.
Yeah.
And you're also getting the spawning output wrong because natural mortality is wrong.
Yeah.
So, yeah. But then once you really have data to inform what's going on, rather than basing it off of the wrong life history estimates, then things get better.
I will say, having done work with the
Yeah.
trolley model, with the
Yeah.
older fund.
Yeah.
Because it's so exploited.
Yeah.
It does some funky things.
Yeah, early
To
on.
get you to the
Yeah.
final endpoint.
Yeah.
If you're changing things around in a weird way, or a way that it doesn't.
Yeah. Yeah. All right. Well, speaking of the trolley model, so now the last sort of part of this talk, I was going to sort of take the Petrali model where we had an environmental index that was developed. So now we no longer know truth. So the benefit of all of this is we know truth. So now we don't know truth anymore, but just sort of dig in and see how one real assessment is behaving. So an oceanographic recruitment index was developed for the 2023 Petrali Soil Assessment. It was not included in the base model that's used for management, but a sensitivity of results to inclusion of the index was conducted. So here now is a table of a bunch of sort of important parameters and likelihoods that the stock assessment estimates. And then their values are going to show up in a minute, but it's a bit overwhelming. So the first column is just the base model. This is what's used for management. The second column is with the environmental index. So this is the environmental index included for all years that it's available. This came from an ocean model, so it started and it's about 30 years long. And then a third one is a run that I did. This was not in the stock assessment, where the index is shortened to 10 years. All right, so here's all of those things. First, I wanted to look at recruitment and natural mortality. And so we can see that when you include the index for 30 years, the unfished recruitment goes up by like 25–30%, which is quite substantial. And the natural mortality also goes up by quite a bit. But if you shorten that index to just 10 years, recruitment is actually slightly lower even than the base model, but quite close. And natural mortality is also extremely close to the base model estimate. And so we don't know the true value of unfished recruitment or natural mortality, but based on sort of the simulations, my inclination is that the base model is probably more correct, and that shortening the time series sort of got back to the correct value. The other thing, and maybe another thing to look at is sort of the likelihoods. So the likelihoods are not comparable because they have different amounts of data. So the index likelihood is completely useless. You would expect the length and composition likelihoods, age composition likelihoods to degrade as you add a new data source, but they degrade much more when the index is 30 years versus when the index is only for 10 years, particularly the length compositions. And so the length composition likelihood is almost identical. Oh, it's actually even slightly lower. The age composition likelihood is almost identical for the base model and the 10-year environmental index, and it's quite a bit worse. And then anyways. The other thing I wanted to point out, we shouldn't be making modeling decisions based on catch advice, but this is sort of the OFL that comes out of these three models, and it's wildly different. And this is a stock that's very close to full attainment. So the difference between these models is really large, and that has a really big impact on people and their lives and their businesses. So it's just sort of important to get right, and these differences are substantial. All right, so now you're looking at the estimates of recruitment, just for the main recruitment deviation period through to the end of the model period. The dark gray box is sort of the 10-year environmental index, and the dark gray plus the light gray box is the full length of the environmental index. And it's recruitment deviations on the left and recruitment on the right. And a few things that I see when I look at this figure are first, the base model in blue and the 10-year environmental index model in yellow are very close to overlapping in both of these figures, particularly before the index appears. Whereas the 30-year environmental index has like way lower recruitment deviations and way higher recruitment, like decades before that index is even in the model. So that is sort of suspect to me that this index is swaying the estimates of recruitment and recruitment deviations when it isn't actually providing direct information on in years 10, 20 years before it's actually providing direct information on recruitment. Another thing that I think this is just interesting. I think, so we can see that there's sort of this recruitment downturn, maybe like 5 or 10 years ago. And the composition data estimates it to be 1 year earlier than the models that include the oceanographic index. So basically all of the models agree that there was sort of a low point in recruitment, but there's some disagreement about what year it was. And I think this is a case where we don't, I'm not sure which one is correct, right? Because there's aging error, and so a lot of this is based on length composition data rather than ages. So, but yeah, so there's this downturn, but it was sort of offset. And then another interesting thing is, so in 2021, the oceanography suggested a large recruitment event. And so you can see that in both the teal and the yellow lines, both in the recruitment deviations and in the absolute recruitment, whereas the base model estimates that recruitment was very close, basically just pulled off the stock recruit relationship in 2021, because we haven't seen any fish that were born in 2021, because the data end in 2022. And so this is sort of an exciting opportunity to sort of see how this played out. And I think, you know, we're probably just starting to see those fish in the survey this summer. And so we can sort of see if that panned out. But sort of keep that sort of 2021 recruitment in mind as we look now at the estimated time series. And so again, the base model and the 10-year environmental model are mostly overlapping during the historical period. They have slightly different estimates of unfished spawning output, but they converge very rapidly. Again, the 30-year environmental index model is a little bit different, as we've discussed. But then when you look at the forecast period, which is in gray now, the two environmental models are now more similar to each other than the base model. And what's happening is that the base model thinks, there was that downturn in recruitment 5 years ago, and then basically since then it has no data to inform anything, to think recruitment has been anything but average. And so whereas the models with the environmental index think that recruitment was kind of high in 2021, and so have a much more positive outlook on sort of where the population is going. And so the forecasts are quite different. And that sort of gets at the OFL for both of these environmental models in 2023, the OFL is quite a bit higher, even though sort of most of the parameter, like the sort of the key life history parameter estimates were quite similar between the 10-year model and the base model. So some of it is sort of actual, so these differences are due to a mix of different estimates of the life history parameters, but also just different estimates of what recent recruitment has been. Yeah, Albie.
Do you also have something, does it have something to do with the initial conditions as well of your model? Because like so the one that has the environment in it predicts a smaller P0 basically, right? So you assume that your reference points would be in a different place.
Mm-hmm.
And so does that play into the different specifications for the OFL as well? And I guess like how do we know if there is like that whole chunk of data of years at the beginning where you have just catch that drives the boat and you have no compositions or anything like how do you know which is right, I guess?
Yeah, well, so I think the base model and the 10-year environment model their B0s are a lot closer.
Yeah.
So I think the idea, I don't, if I were a betting woman, I would not bet on this teal line. I think it's probably too low. I think it's probably somewhere closer to the yellow blue line. Yeah, Melissa.
So one thing you could do is plot the uncertainty from the base model here.
Oh yeah.
Because
those are
something that's important for discussion in practice.
Yeah.
And I'm guessing that all of those lines are kind of within the range of uncertainty.
Totally.
So that data can't really discriminate between a lower B0 and a higher stock size or a higher B0 and a lower stock size until you have the data. Comp data. Yeah. And so we should just accept that we don't know the things we really wish we did.
Yeah. Right? Yeah. That's also true. But I think yes, I think you're correct. But I also think the simulations indicated that there is likely some bias
that's a problem.
in the bottom line.
But even if you just use this environmental model as a sensitivity, it still plays into the risk discussion.
Yeah.
With council. And
Yeah.
how that gets translated to
Right.
management when you're forward looking and setting catches with
Totally.
any additional.
Well, and I think that goes into the forecast, right? That these, even though the teal model, this like 30-year environmental model maybe has some problems, you know, it has a much rosier view of the forecast. And part of the reason it has a rosier view of the forecast is because it actually does think recruitment has been good recently. And that's like real, like data.
And that's the actual, the real value, I think, of these indices is what's coming.
Right. Yeah. And in fact, so because the index wasn't in the base model, we did sort of like a practice risk table for Petrali in 2023, and we included the results from this index that said that recruitment has been quite high recently, and so Petrali scored scored sort of like great environmental conditions in the risk table. And you know, they don't like to use risk tables on the West Coast yet; they're not quite ready, but it would have led to like more catch opportunity. It would have not led to as much more catch opportunity as using the model as a base model. Yeah, Luigi.
I'm not sure if I missed this from earlier. So when you were talking about the hindcasting course, so do you do like a retrospective where you peel 1 year off each time and then see what that recruitment forecast was with it?
No, that's a great idea. That's in the next slide. These are well, I guess this is the real Petrali model. So previously, everything I showed was simulated. So only, you know, these are the only 3 slides of real data. And so we do fit retrospective models. I think, well, I'll just like cut to the chase here. I think we underutilize our retrospective models. And so we, you know, at least what we mostly do with them is we sort of do our 5-year retrospective models and we calculate Mohn's row and we hope there's no evidence of retrospective bias. We sort of move on. But when you think about sort of well, first of all, I think people are still figuring out how to decide whether to include environmental index. So like on the East Coast, when they're doing model selection on whether or not to include environmental variables in their stock assessments, they use AIC. At least that's my understanding. And I think that's going to underrate the benefits of this index because AIC is not like these indices are not going to help them describe historical data better. And when you look at like the time series modeling community, they sort of acknowledge that there's multiple uses of models. And if you want to use a model to forecast, you should use one set of sort of model selection metrics. And if you want to use a model to understand sort of historical dynamics, you should use a different set of model selection metrics. And stock assessments are really just like nonlinear time series models. And I think we're interested in both the forecasting and the historical, because the fits to understanding the historical dynamics helps us with reference points, but the forecast is what we use sort of to set management advice. And retrospective models really are just sort of leave future out sort of models. And so we could be using these model runs that we're already doing and looking at how the fits to length composition data are changing, you know, length and age composition data are changing in a 5-year retrospective model run. So I think we're sort of leaving a lot of information on the table. Yeah.
I guess, yeah, kind of like related to that, right? Because you're I guess the plug for this is that you're improving short-term recruitment.
Exactly.
How well did it actually?
Exactly.
If we take out 1 year of data.
Right. Yeah.
I had another thought and I forgot it.
I mean, I think what we're really getting at is evaluating forecast skill, which we don't really do in stock assessment.
Exactly.
And we need to kind of adopt some tools from the oceanographic community.
And just time series community.
Yeah, forecasts, understanding forecast skill.
Yeah. And I think we're actually part of it. Like, I think the retrospective models are that. Like, we're fitting the models. I don't think there's like new models that we need to fit. I think there's just like new diagnostics we need to use to existing model runs that we're doing. Yeah, exactly.
Tell us what those are.
Well, that was sort of like my aha moment after just like digging my brain into simulations for too long, was sort of like, this is what we should do. But I think it's really the same metrics that we're using, right? So you just, right now we look at fits to historical length composition data. And now, but we should also be looking at forecasted fits to length composition data. So I'm not even sure the diagnostics and the metrics are really that different than what we're using. We should just be looking at them in a forecasting context rather than a hindcasting context.
I guess I would be interested in seeing that for the simulated data too.
Yeah. Yeah.
Just how well you actually did.
Yeah, that's a good idea. I could take my own advice. I think I wrote this, I think I had this sort of aha moment after I had done all the simulations, and I was like, oh, we just need the retrospective models. So now I can add that to paper though. Yeah. All right, so I think a few other things. So my original idea was to explore these patterns sort of across a range of life histories and selectivities. It is a fair bit of work to get to sort of simplify these production assessment models so that they sort of simulate well and quickly. But if you have an existing stock synthesis model that you use for MSE or simulation, I'd love to chat. I've been working with the sardine model, but was not quite able to get it ready in time for this talk as well. So that would be a really different example. And they only do 1-year forecasts for sardine rather than 12 years. Yeah, Melissa.
I think another approach is to, and Juliet can expand on this, but is to really look at what TNB offers with respect to being able to estimate random effects.
Yeah.
And just kind of.
Well, yeah. I mean, I think in general, I agree that TNB is the future. I think for this paper, I'm sticking to stuff.
You have to put go on it.
Exactly. Yeah. I totally see the value. I totally agree in the value of that. I just need to sort of constrain it a bit. And I think, you know, there's not. I think right now the like software for doing stock assessment in TNB is still somewhat limited in terms of like the bells and whistles that you can include. You can develop your own custom model, obviously, but just in terms of sort of like reproducible software.
The other assessment you should look at is sablefish.
Yeah.
Right. I mean, we've already done some of this, but in past stock assessments, one of the biggest questions was, do we use the historical tide gauge data for recruitment?
Right.
Or not?
Yeah.
And do we basically tune the index out of the model during the historical period with data or not? And if you can answer those two things,
yeah,
I think that will be incredibly helpful to whoever draws the short straw on the next
round.
I think
that's she's sitting here. I mean, so one thing about the sablefish assessment, so with, I mean, this is getting really down into the weeds, but with the Petrali assessment, where it came from the oceanographic index, figuring out the input standard error is relatively straightforward, and you can just use the prediction error from the regression on, you know, the oceanographic time series. But the correct input standard error from the tide gauge data is really unclear, because like what I've looked at the stock assessment, what's in there what's in there is just the standard error from the DFA, which has nothing to do with how well it predicts recruitment, which is why you estimate the added standard error. But the correct input standard error is hard to know.
It's not clear. There's no easy answer.
Right.
Yeah.
Right.
I think the secondary question too, if you're going to look at something like sablefish, is what is the benefit of an environmental index?
When you see them so
really you see them, because sablefish, you see some age 0 in the survey with Petrali we do.
Right.
And so is that age 0 look in sablefish sufficient?
Right.
And so kind of peeling back
right.
and selectivity in the survey.
And for a question like that, I'm not even sure that I need to like do the sablefish model. Mm-hmm. You could just change the selectivity of sort of the existing model. I like played around with the COD model originally. Actually, the one that's in SS3 Sim has like pretty early observations of the population, and I didn't want to set myself up for failure, so I pushed the selectivity curve to the right a little bit, but I could push it back down to the left.
I mean, for sablefish, the real use is like the catch plus climate forecast period where we only update these models infrequently. And so you can still turn the crank on a harvest projection potentially with whatever your climate index of recruitment is and catch and get better advice than what you, like the forward look is the disease. Because yes, please see H0 fish.
Yeah.
It's an amazing thing.
Yeah, I think you're kind of getting at this with like your early retrospective work that didn't work out.
Right.
Is because on the West Coast, we do, like Melissa just described, we do catch line projections where you have add recent catches.
Yeah.
But could we do catch line projections plus
Yeah.
environmental index models?
Right. Projecting index.
Like building up our toolbox
Yeah.
of improving management advice depending on.
I mean, technically that's in the terms of
Yes,
reference.
you can, because I lobbied for putting that.
I don't think any of them are done, so I've never.
Well, it's never been applicable.
The management framework is set up to be able to use it.
Yeah.
I think that's a
It's a sucky thing to do on stuff.
That's what I was wondering how you implement it.
It sucks.
Yeah.
Sorry. You have to iterate like 1 year at a time to get it.
Oh.
To get the right information. So we're going back like to where we were 15 years ago, right?
Yeah.
And so it's not simple. I talked to Rick.
Yeah, like I said.
I don't think
Yeah.
it's changed.
Yeah.
3 or so years.
I think, yeah. Leach.
This is not totally related,
Yeah.
but like when you were talking about that 10-year, just thinking the last 10 years,
Uh-huh.
I guess if you were to give advice, would you see that as like a moving window of 10 years? Or do you think it would start from 2014 or whatever? And then just
No, I think it's terminal year minus 10. Yeah, that's what I would say. That's like these models, so other next steps, so potentially looking across either adding a wider range of models or just changing selectivity in the existing subset of models. Right now, catchability is correctly fit. Catchability for this index is a very weird thing. You're not catching anything, but there is a scaling parameter. So right now it's not being estimated. And the new release of stack synthesis actually has some like better catchability options for these kind of indices that I haven't played around with. So I don't know if that's going to get done for this or not. I would love to understand what's causing the bias in these productivity and scale estimates. But I feel like I've talked to Rick about it a lot. I've not been able to figure it out, and I feel like I've done a lot of model runs, and I just can't figure it out. So I'm at least happy that I've sort of figured out a solution, even though I don't think the solution actually has identified the mechanism. So I guess some conclusions are that, so I think the environmental recruitment indices did improve estimates of recruitment at the end of the time series. I think the absolute amount of improvement, and it also improves sort of our forecasts as well. And the absolute amount of the extent will likely depend on specifics of the assessments. And then I would say only include recruitment index as a survey for years at the end of the assessment period. And I already went on this. I already talked about that. So, yeah. Any other questions? Albie.
Can you talk a little more about how people go about selecting and designing an environmental index for recruitment? Is that stuff specific? Is that place specific? Like, what's the thought process or the research that is needed to say this environmental index from this oceanographic model is why it drives recruitment?
Yeah, so I think there's like a lot of research on that right now as well. And I was just sort of painting over all of that and just was like, you're a stack system scientist, someone handed you an index, how do you use it? But I think, the way, Melissa probably can speak to this better than me. The way it's been done on the West Coast is sort of, there are done a bunch of different ways that you can do it. On the West Coast, the way that Melissa and Nick Tulameri did this was sort of, they identified where fish were in the ocean at each of their life stages, and then took from ocean models things like temperature and transport variables from, you know, those locations where they were at the correct time in their life history. And then they did sort of like a dredged AIC model selection kind of procedure where they also making sure to minimize multicollinearity, sort of keep models somewhat simple. And so that was what they did. I think there's some concern that there's a little bit of circularity because they're using, you know, those approaches generally use recruitment deviations from historical models as your response variable in the regressions. And I think one benefit to this approach is, right, so I'm saying only include the index for the last 10 years of data. And that's great because you can also avoid the circularity because you can just say, I'm not that whole regression procedure. I'm not going to include those last 10 years in the regression procedure as either. You're not throwing out a ton of data because not even all of those 10 years you're not going to have recruitment deviations that are good for those full 10 years anyway. So you're not throwing out a ton of data and you could sort of avoid that circularity a bit. And so we have our CEFI stock assessment scientist, Megan Fettern, who I think is online, has been sort of working on sort of further developing methodology around how we do that. In Alaska, where you just have like bazillions of people sampling the ocean at bazillions of different life stages, I think, you know, you can sort of, you know, what they've been looking at are these structural equation models where they can sort of, but that it helps that they've sampled the population at a lot of different early life stages to do that. I don't know, Melissa?
I think you pretty much got that right. I mean, we went through each life history stage where we had old research studies and said, well, what do we think would impact survival at each stage? And then we built kind of a standard regression type modeling framework to say, you know, which of these hypotheses that we've outlined ahead of time seem to hold some weight.
But I think it's like a very active area of research, and there's like, yeah.
There's probably better ways to do it, but I think getting your XYZ time space for your selection of your environmental data is what matters most.
Yeah.
Probably, whatever tool you use. And frankly, if you're right, and we only need the last 10 years of the climate time series, you have solved the issue with the lack of historical satellite data.
Yeah.
Actually have recruitment.
I mean,
estimates. So
I think it's still an issue because, like,
you have to build a relationship.
Exactly. Like, I think Megan has been trying to build a relationship for yellowtail rockfish, and there's just like, she's like 20 data points.
Oh, black rockfish, like some of the near shore.
Yeah. Well, yellowtail has, I think the recruitment estimates from the historical the yellowtail assessment is very good. So there's like very good recruitment information from the like last assessment, but she just only has like 20. She only has 20 data points. She could go back, the recruitment estimates go back farther. It's the satellite data that she only has.
Yeah. Metrology assessments, the best data set on the West Coast.
Yeah.
Because we fish the daylight out of it.
Yeah.
And it recovers.
Yeah.
And it doesn't live that long. So
Yeah.
that's like, that'd be my start.
Yeah. But honestly, like yellowtail doesn't live that long either. We didn't fish the daylights out of it, but we like fished it fairly hard, and it is fairly short. It's like pretty short lived for a rockfish. So they age. They're really easy to age.
Nick would probably bring this up, but you know, some of the visual surveys that they do for rockfish could also serve as indicators, so that gets you out of that kind of doom loop of having to use model estimates.
Yeah. We've been looking at a lot of, I think those surveys are not as long. So I think they have their Olympic Coast dive survey. I think Megan's looking at that. ODFW has these SMRF surveys. So I think we're planning on looking at that. The time, like the longest time series is the stock assessment. The longest continuous time series is definitely.
We have a question from Grant Adams. How well do environmental indices improve forecasting biomass, or more importantly, SSB, given maturity and weight at age?
Well, maturity and weight at age were correctly specified in all of these simulations. So I guess I don't know what would happen if they were specified wrong. Does that answer his question? Or is he telling me I should do a whole nother axis of these simulations with like maturity and weighted age?
Grant, if you want to clarify, you can also unmute. You should be able to do that. More of, do these recruits matter to total allowable catch advice?
Oh, yeah, 100%. And I think, this gets at it. Like the total allowable catch is 3,100 metric tons, 4,200 metric tons, or 3,400 metric tons. And that's the OFL in 2023. So that's a huge difference. And that's for petrale. And I think I haven't, that's a good point. I should actually quantify what's going on here in these forecasts. But you can see that, in the forecast period in gray, in general, the darker bluer colors have lower error than the lighter orange colors.
When you apply the orange ones first, so that blue shows up.
Yeah. I don't know how to do that because ggplot just sort of, I guess you could change the factor order, reverse the factor order.
Turn on alpha, I guess.
Well, yeah, I think if you reverse the factor order, it would switch it.
This is for the 10-year environmental and
What?
this is for the short-term environmental.
Yes, the dark ones are the short one, and then this is the long one, where in the light pale colors are the crazy 30-year one. Yeah. Oh, either one.
I was a bit curious about this, like, short-term, like, the fact that you shorten your environmental time series. Does it change something in the, I'm not very sure to have understand how you're linking your environmental index to your equipment, and does that change how how they are linking to each other when you use 30-year or 10-year?
Yeah, so because you're doing it, I think in TMB, right, with Cole's Pollock model. Yeah, so go back to the equations. So I think this is the way that it's sort of implemented in Cole's Pollock model, is you have your actual recruitment function, rather than just being a function of spotting output, is a function of spotting output and the environmental variable. The way it's implemented, the easier way to implement it in stock synthesis, which does not estimate random effects, is that your stock recruit relationship is unchanged. It's just sort of a very plain old stock recruit relationship. And then you just assume that the environment is sort of an observation with some amount of observation error of these recruitment deviations. So you don't need to have an observation of the recruitment deviation in every year of the model. You can have missing data, you can have short time series, you can have long time series. It's like a survey. Does that make sense? Does that answer your question?
So when you're using 10-year versus 30-year, is it changing your G or your sigma and Y?
No.
Everything is okay.
No, yeah, so well, the sigma Y in theory could be different every year. You could put in a separate, you could put in so that's an input standard error, and it could vary by year. But the G is like the catchability basically, so that will be fixed. And then it's just sort of an observation to help you better inform your estimates of epsilon is like the idea. Melissa.
I mean, not for this paper, which you're trying to finish.
Yeah.
The other simulation stuff is
Yeah.
to do this with the real, like simulate based on real data, the integrated.
Right.
The dynamic
This one.
part of this.
Yeah.
And see if you can come up with some advice for how to deal with sigma R when you have
Right.
a environmental.
Yeah.
And the stock.
I feel like ADMB is not long enough for the world that you like.
The better way to do it is.
Yeah. And then you don't need to provide the advice on sigma R.
Yeah, that's true. That's not possibly you're gonna kill it.
That's true. Yeah. Yeah, Lychee. Oh, no, yeah, Josh was, yeah, you already had it.
So you showed the OFL estimates for each of these models. Is the uncertainty taking OFL similar across all of them? Or is adding environmental, or is adding the environmental indices increase the OFL uncertainty?
I do not know. That's a good question. My guess is, yeah, I don't know, because I could imagine it gets smaller if you have the, if the likelihood, if it thinks that the likelihood, if it's more confident in the recruitment deviations in those final years, I could imagine the OFL estimate going down. But Lychee.
It was related to Juliet's question. And
Yeah.
I mean, so yeah, the relationship is fixed over time, so it would make sense that if you include the 30 years, the relationship with recruitment and that index at 30 years ago would look very different from now.
Yeah, and so in the simulations, I'm not even dealing with the simulations are perfectly stationary. The relationship holds up over time. So that's, I think, another, that's one benefit of only including 10 years, is if you can figure out a way to develop, I think figuring out a way to sort of identify the correct drivers in a non-stationary, the correct drivers today, based on a non-stationary relationship is difficult, but if you can do the statistical magic and figure that out, the fact that you're only including the driver for 10 years is sort of going to be more robust to a non-stationary environment. But I think, yeah, doing the earlier work that Albie was asking about gets very hard in a non-stationary world. Yeah, Juliet.
How did you come with 10 years? Like, is it based on something about the bias graph or something, or is it
Nope, I just sort of tried a few different values. I think I originally tried 5, and then I was worried that was gonna, and it worked obviously, and then I was worried that you're gonna have some problems estimating like catchability with a time series that short. So I was like, oh, I wonder if 10 will work. And it did.
Generation time.
Yeah, well, yeah, I mean, but the generation times for cod and petrale are different. So, and it was pretty effective for both. So
difference 5 and 10 years?
no, I could imagine it would, what I would imagine it might be more related to rather than the generation time is like the total number of years in the assessment. So that's fairly similar. Just like your total, because what you're doing is you're just reducing the weight of this index and the likelihood, and that's all relative to all the other data and the likelihood. And so I think it's, yeah, like the sardine model, they only run it for like 20 years or something. So I could imagine, 10 years versus 20 years, 10 years for the sardine model might cause more problems than 10 years for a 100-year assessment model. Yeah, that would be my intuition.
I feel like that famous example would be the Bay of Biscay sardine, right? Where their environment relationship broke down.
Yeah, well, also the Pacific Coast sardine too. Yeah, yeah. So Robert Wildermuth sent me there like the West Coast sardine MSC model. So that's what I was trying to use, and I was hoping, since it was like, I was hoping it would just sort of like smoothly integrate into SS3 Sim since he had used SS MSE, but it turns out they're like just different enough to cause enough headaches that 2 days was not enough time, and that's all the time I had. Yeah, Juliet.
So if shortening your environmental time series is the way of changing the weight in your likelihood, do you think it would make different results if you were playing with that? Because you can modify weight of your data time series, right? Yeah,
well, for an index, usually you only modify the weight based on the standard error of the index. So like what I haven't explored doing, for example, is right now the standard errors of the index are all correctly specified. So one thing I could do is take like a really good index that's sampled at a standard error of 0.05 and then input it with a standard error of 0.2 and do something like that. So artificially basically inflating the standard error of the index. And that, my intuition is it would have a similar effect on the bias issues. I don't know what would happen to the forecast, because whether it would sort of ignore the index more and the forecast would become less skillful. That would be my question.
We have a couple questions online. Megan, if you want to go ahead and unmute, you can go ahead and ask your question.
Hi, sorry guys, I was gonna jump in when Kiva, this is Megan Federn, by the way, I'm the one working on environmental indicators for the Yellowtail assessment. I was gonna jump in, but I'm a GoToWebinar novice, so it took me a little while to find my control panel. So this is kind of circling back to something else. But I just wanted to add, like, one interesting thing that I have been finding, and I think, you know, other folks are finding with some of the other assessments, is that when you start to transition away from like leave one out cross-validation or from AIC, the leave future out cross-validation tends to be like extremely sensitive to whatever your training data set is, which, you know, of course makes sense. But then when you're working with only 10 years of data, your training set is very short. And then also whatever years you're predicting is very short. So your RMSEs are coming from like very small amounts of information. So one thing that I've been thinking a lot about is like the benefit of cutting the data sets, like Kiva said, shortening these to just 10 years of data. But perhaps when you're using such short data sets that it might be more beneficial to use leave one out instead of leave future out. So I've been trying to look at some of those trade-offs when it comes to shortening the 10 years. And then to Leachy's point, I actually do think there is some potential to fitting non-stationary models with such short time series. Like, I don't think you could reliably estimate a slope with something like a DLM with these like lengths of these time series, but I think there's potential to do like a temporally structured GAM that could account for some of the variability that we get in these relationships through time.
Okay, Maya, if you want to go ahead and also unmute, you can go ahead and ask your question.
Sure, yeah, can you hear me okay?
Yep.
Oh, great, awesome. Yeah, thanks, Kiva. This is really interesting work. So I had kind of two questions arise. The first, just really a thought about this slide. My hunch, based on what I heard, is that those, you know, freaky models, I'm guessing the production function is probably going awry. There's maybe just too many different things. I think that kind of came out in the discussion, but I would just yank that plot and that would be my guess of what's going on there. The main thing I wanted to kind of ask is, I sort of had a different interpretation of your results with the base environmental and tenure index. It appears to me like we could also interpret that, especially looking at the figure, you know, I hadn't looked at this table super closely, but it could just be that your tenure index is uninformative. And so I think Juliet and folks were maybe getting at this earlier, but you know, what would be like convincing here is if you did sort of the full cross of the year, you know, maybe like in 10-year or 5-year increments of the time series, and then dialing up and down the standard error that you're putting into it. Because in the absence of an operating model that you are really confident about, like, is this right? Is this true? Whatever, like, we're never going to get there with this. That's fine. It's just hard to know whether you've just added a light sprinkle of noise and that's it. Because, you know, comparing M, for example, between those two models doesn't necessarily tell us that that 10-year index is a better, you know, is doing something great. It might just be doing nothing.
Well, I don't think the index should be informing the estimate of M.
Mm-hmm.
Do you think it should be?
Not, I mean, ideally not if you're hoping it's tied directly to recruitment, but it's just hard to know if it's actually doing anything. I mean, I think this is one of the questions you had at your initial slide, which I thought was really good, which is how do we know if there's improvement happening?
Well, so I think what the simulation showed is that there is improvement happening. We are doing a better job estimating recruitment at the end of the model period. and we are doing a better job forecasting the population when we include the index. And so I sort of took that as sort of face value, that these indices do improve the estimates of recruitment and the forecast, and then sort of just compared the models. Yeah.
Yeah, that sounds reasonable to me. I guess I just think that there are lines that could be filled in here that could make that point more strongly just by making a couple of those tweaks.
Yeah. I think I spent most of the work on the simulations, and then I was like, well, let's just see what happens when we try to fit a model.
For sure. Well, that's always how it goes.
Yeah. But I guess my thought is like, you're right, we don't know what the true value is. That, I think that the 30-year index is likely leading to bias in unfished recruitment and natural mortality in the Petrali model. And that's not based on what I'm seeing in the Petrali model, that's based on what I saw in the simulations, and then seeing that the expected result from the simulations is appearing with the Petrali model. So like the fact that unfished recruitment and natural mortality are higher, that's exactly what you would expect from the simulations. And we're seeing that in practice with the Petrali model. And then with the Petrali model, we're seeing, again, just like you would expect from the simulations, that when you shorten the index, there were estimates of unfished recruitment and natural mortality go down. So that's really all I think I was trying to show with the Petrali model, was sort of that like what we saw with the simulations is what we see in practice as well. And yeah.
Awesome, thanks.
We also have a question from Christine Staywitz. What is the range of quality of the indices you explored? Did you identify a threshold of quality below which results weren't promising?
Yeah, so I used the index standard errors. This is the standard error of, go back to the equation. There are faster ways to do this. Okay, so this sigma y, that sigma y ranged from 0.05 to 0.5. After 0.5, I stopped seeing much of a difference, so I stopped running. I did some initial like scoping runs with the sigma above 0.5, and I didn't see a difference. I also, the sigma R for both of these populations is right around 0.5, so I think that works into it too. Like sigma R for hake is like 1.2, so you might be able to get away with like a less skillful index for something like Pacific hake. So that was the range. At above 0.5, I think it was useless. Oh, and the other thing I was going to say is, so for the index that was developed for Petrali, I think the correct standard error for that would be around 0.2. So this is sort of like a realistic range. Yeah, Melissa.
You're finding that above 0.5, not so useful, aligns with other literature that found essentially similar results.
Yeah,
so
great.
You are in.
Excellent.
Yeah, sorry, can you all hear me? I asked that kind of like before the whole discussion about it, which kind of answered the question. But after that discussion, I was wondering about the G function in here, and if you looked at different types of functional relationships.
I have not, yeah. And so I'm currently using an older version, not an old, but just like a year-old version of stock synthesis, where the G function is just like a linear term with a single catchability parameter. And the new release of stock synthesis allows you to also estimate an intercept, which is particularly useful for these like, it's a deviation vector. So even if you constrain the directives to sum to 0, you wouldn't necessarily expect they're going to sum to 0 over the period that you have the index. And so I'm potentially considering, depending on how much work it is, updating this to sort of the new version of stock synthesis so that I could at least use that sort of linear function, or the 2-parameter linear function, rather than the one parameter linear function. Yeah, Josh.
So I'm wondering how to use these in practice for forecasts, because at the moment, all the data looks like your forecast period, you have some real knowledge of what the recruitment estimates are, because your forecast period has been like 2019 through 2023 or something like that.
Mm-hmm.
So you have some estimate, but obviously when we do forecasts, we're actually forecasting out until 2025, 2030. Presumably we don't have environmental indices in the future.
No.
So I'm wondering, and I assume you're getting it from a model output. So any model output.
So these forecasts don't include the index in the forecast period.
Okay.
So the index gets cut off the same year all the other data gets cut off. It's just that you're doing a better job estimating recruitment in those last years where you don't have other sources of data. So that's where the benefit is coming from.
And then you're updating R0 and whatnot.
Yeah.
So you get to
Yeah.
The actual forecast period.
Mm-hmm. I think there is a hope, like the Climate Ecosystem Fisheries Initiative is looking at medium-term forecasts that would operate on these like 5 to 10 year timescales. From talking to oceanographers, those are also like by far the forecasts that they have the least faith in.
Mm-hmm.
And so I don't, it would be cool to have, we should totally build assessment and forecast tools that can incorporate forecasts of ocean conditions. I don't think the oceanography community is quite there yet to provide us with something that's like skillful.
Okay, that was what I was wondering was what happens when the oceanographic variables, you have no idea what's going on with the future, but forecasted for management.
Yeah. And I mean, another reason to include them in a forecast module is like these catch climate projections, because technically when we do those, we are just updating, even though it's real data and it's no longer really forecasted, we're updating the forecast file. That's the only bit that's getting updated. So that would be just like nitty gritty and another reason to think about them in forecast. I think retrospective models are another place where you can like play around with that as well.
If anyone has any questions online, go ahead and you can unmute yourself or send something in the chat. Okay. In that case, I want to thank Dr. Oken again for coming and giving a wonderful think tank again today. We should have another presentation in 2 weeks from Caitlin Allen Askelrud. That will be virtual, but for those who are able to come into SAS, we will all be here to enjoy that here in Fish 203. So again, I want to give Dr. Oken another round of applause. See you all hopefully in 2 weeks.
You can all go back to doom scrolling now.
Yeah. Oh, Grant wants to know, what's your favorite place to doom scroll?
My favorite. I've been really hardcore avoiding doom scrolling this year.
Good, good. That's not a bad thing at all.